Welcome back. We are continuing our course on calculus of vector functions. In the previous video, we learned how vector functions describe curves in space and how to visualize them. Now it's time to bring calculus into play. In this lesson, we will explore how limits, continuity, and derivatives extend naturally to vector-valued functions, and discover what they tell us about motion and direction in 3 dimensions. If this video helps you, don't forget to like this video, subscribe to the channel and turn on the notification bell for more videos on math from basic to advanced. Share this video with a friend who's studying calculus. Are you ready? Let's dive in. Let's start with limits. The limit of a vector function r of t as t approaches a value c exists if and only if the limits of all its component functions exist. This can be written formally as follows, where L is the resulting limit vector. Because of this equivalence, the process of finding the limit is straightforward and surprisingly simple. Since a vector function is constructed from component functions, it is enough to calculate the limit of each component separately, using the standard rules of scalar calculus. In summary, the limit of a vector function is found by taking the limit of each of its component functions individually. So the process is exactly the same as in single variable calculus. You just apply it to each coordinate. Let's find the limit as t approaches 0 for the following function. The first component approaches 0, the second component approaches 1, and the third component approaches 1. The red dot on the curve marks the limit point at t equals 0. Now that we know how to calculate the limit of a vector-valued function, we can define continuity at a point for such a function. A vector function r of t is continuous at point t equals c if the following 3 conditions hold. The function must exist at the point c. In other words, there can be a hole or break in the graph at this specific point. The limit as t approaches c must exist. The function must approach the same height from both the left and the right. And finally, the limit must equal the function value. This simply means the hole is filled in and the graph is a seamless curve. The key takeaway is simple. R of t is continuous if and only if all of its component functions are continuous. If one component has a discontinuity, the entire vector function is discontinuous. Determine whether the vector function is continuous at t equals 0. Explain your reasoning. First, we find the value of the function at t equals 0 by substituting t equals 0 into each component. Since the y component of the vector function is not defined at t equals 0, the entire vector function is discontinuous at t equals 0. Let's look at item B. We will test the continuity of vector function at t equals 0. We find the value of the function at t equals 0 by substituting t equals 0 into each component. At t equals 0, all components are defined. Next, we find the limit of each component as t approaches 0. At last, we compare the results of test 1 and test 2. Since the limit equals the function value, the vector function is continuous at t equals 0. Next, we will talk about derivatives. Now that we've seen how to calculate the limit of a vector function, the next step is to learn how to calculate the derivative of a vector function. The derivative of a vector function measures how the position vector changes with respect to t. It is defined as follows. The vector function has a derivative, is differentiable at t if x, y, and z have derivatives at t. The derivative is the vector function. Fortunately, like limits, the calculation is done component-wise. To find the derivative dr dt, you simply take the derivative of each component function. To prove this, we begin with the formal definition of the derivative, which is the limit of the difference quotient. We then immediately substitute the vector function with its three scalar components. First, we perform the vector substitution in the numerator, which is done component-wise. Then, because dividing by the scalar delta t is the same as multiplying by its reciprocal, we can distribute that scalar division to every single component. This gives us three separate difference quotients, all inside a single limit. Since the limit of a vector function is simply the limit of its components, we can move the single external limit inside the vector brackets. We now have three separate scalar limits, one for the x, one for the y, and one for the z component. Each of these three scalar limits is the exact definition of the derivative from single variable calculus. Therefore, we conclude that the derivative of a vector function is simply the vector composed of the derivatives of its component functions. Let's look at the geometry. The geometric meaning of this definition is shown below. We have our curve C at two distinct instants, t and t plus delta t. We have two position vectors, r of t and r of t plus delta t. The vector connecting the terminal points from P to Q is the difference vector r of t plus delta t minus r of t. This vector lies on the secant line passing through P and Q. Now we divide the secant vector by the scalar time interval delta t. This calculation gives us the average rate of change between P and Q. It still points along the secant line. This is where the calculus happens. We take the limit as delta t approaches 0. As Q overlaps P, the line connecting them transitions from a secant line to a tangent line at P. Let's see how it works. For the curve, find the derivative, sketch the position vector, and sketch the tangent vector. This problem asks you to perform three main asks for the given vector function. Find its derivative, and then evaluate and sketch the position and tangent vectors at t equals 1. To find the derivative of a vector function, you simply take the derivative of each component function separately, with respect to t. To calculate the position vector at t equals 1, you substitute t equals 1 into the original function. The position vector is a vector that starts at the origin and ends at the point P with coordinates x equals 2, y equals 1, and z equals 0. The tangent vector tells you the instantaneous direction and rate of change of the curve at the point P. To calculate the tangent vector, r prime of 1, you substitute t equals 1 into the derivative function. The tangent vector at t equals 1 is placed at the point P. It points in the direction 2, 2, 3. This means, starting from P, the vector extends 2 units in the positive x direction, 2 units in the positive y direction, and 3 units at the positive z direction. Before we finish, there's one more idea that will be very important later: the unity tangent vector. Think of it as the pure direction of the curve at each instant. Why is this useful? Because later, when we study curvature and acceleration, we will need to separate the motion into two parts: the speed at which the particle moves along the curve and the magnitude of the curve. The unity tangent vector is the key that allows us to make this separation. We can express the tangent vector at point P as the product of its magnitude, also called length, and its direction. The norm of a vector is a measure of its magnitude or length, often represented by double vertical bars. It is calculated by taking the square root of the sum of the squares of each of the vector's components. The unity tangent vector has a magnitude of 1 and points in the same direction as the tangent to the curve. The equation for our unity tangent is capital T of t equals r prime of t divided by the magnitude of r prime of t. For the vector function, write the tangent vector as the product of its magnitude and its direction at t equals 1. Prove the unity tangent vector is a unit vector. This problem requires 3 main steps. Step 1. Find the tangent vector at t equals 1. Step 2. Express the tangent vector as the product of its magnitude and direction. And step 3. Prove whether the tangent vector is a unity vector. Let's do this clearly, step by step. I've used the vector function above to solve the example faster. We are given the vector function. Compute the tangent vector and then evaluate it at t equals 1. Next, compute the magnitude of r prime of 1. The magnitude of r prime of 1 is equal to the square root of 17. Now we find the unity tangent vector. The unit tangent vector is found by dividing the tangent vector by its magnitude. At last, write the tangent vector as the product of its magnitude and the unity tangent vector. To prove that the unit tangent vector is a unity vector, we must calculate its norm.